It is well known that when a ship is sailing in following and quartering seas, the ship's motions will be augmented and the possibility of it capsizing will be increased when compared to sailing in against or beam seas. It is therefore important to possess more detailed knowledge about these risks for safer navigation in following and quartering seas. The ship handling techniques that we are to study here are also available in the International Maritime Organization Circular Guidance to the Masters for Avoiding Dangerous Situations in Following and Quartering Seas. According to the guidance, risks in following and quartering seas may arise when a ship is sailing in the same direction and at the same speed as the problem waves. Let's take a close look at the effects of these seas upon a ship's stability. The situations that should be most carefully monitored in following and quartering seas when the ship is traveling in the same direction and at the same speed as the problem waves are the encounter wave grouping phenomena, parametric rolling, the reduction of stability, and the broaching to phenomenon. These four serial phenomena are the characteristics of encounter wave grouping phenomena. First, let's take a look at encounter wave grouping phenomena. Ocean waves are an integration of irregular waves comprising those of diverse lengths, heights, and directions. Encounter wave grouping phenomena occur when a ship is sailing in rough seas that involve irregular waves with sudden serial high waves attacking the ship regularly from aft. This means that when a ship is sailing in the same direction and at the same speed as the high wave group, the ship might be constantly hit by severe serial high waves. This is called the dangerous encounter wave grouping phenomenon. To avoid dangerous encounter wave grouping phenomena, it is essential to eliminate the speed conditions that cause such phenomena. As suggested by many experimental results, the most probable condition a ship might be caught in dangerous encounter wave grouping phenomena can be expressed by the formulae shown here. A combination of encounter angles of the ship to the wave coming from the aft, the ship's speed, and the wave period. According to the IMO's ship handling guidance, a dangerous zone is defined as VT being 1.5 as the norm with a range between 0.8 and 2.0. If your ship is in the dangerous zone as defined by a combination of the ship's speed and the encounter wave period, countermeasures are imperative. Therefore, you must remove the ship from this danger zone, allowing the waves to pass by without doing any harm and avoiding the dangerous encounter wave grouping phenomena by reducing the ship's speed or by altering course. Next, we'll take a look at parametric rolling phenomena, one of the operational parameters endangering a ship in following and quartering seas. When a ship proceeds through regular longitudinal waves, the ship rolls repeatedly, for instance, to the starboard side on the first crest and to the port side on the following trough. However, when parametric rolling occurs, a ship rolls to the starboard side on the first crest and to the port side on the following crest, which means that one rolling cycle is completed for every 2 wave cycles. Consequently, the amplitude of the ship's roll is gradually magnified. To understand this more easily, Let us compare ordinary rolling and parametric rolling. When you look at these motions more closely, you will notice that the ship rolls only once for every 2 cycles of passing waves, while the ship pitches once synchronous to the cycle of passing waves. This type of rolling is magnified when the encounter wave period reaches half of the ship's natural rolling period. This means that as GM decreases, the probability of parametric rolling increases. In order to avoid parametric rolling, it is necessary to adjust the encounter wave period so that it does not coincide with 1/2 of the natural rolling period of the ship. In other words, when the ship rolls once while pitching twice, you should reduce the ship's speed as much as possible to maintain her course upon judging the ship is subject to parametric rolling. Next, we will look at the dangers resulting from a reduction in stability. While sailing in following and quartering seas, great attention has to be paid to the reduction of stability. The degree of stability is determined generally by the area of the waterplane as previously shown in the chart. For instance, if a ship rides on a crest equal in length to the ship's length at midships, stability is reduced as the water planes at her bow and stern decrease due to the lower water lines at both ends. On the other hand, when a trough of the same wave passes the midships, stability is increased as the water planes at her bow and stern increase due to higher water lines. Even if a ship is in a situation with reduced stability, the time span the ship might endure this will be shorter when sailing in counterseas. Conversely, the possibility of risk is increased in following and quartering seas, as the time span is greatly increased. Now let's see how to avoid the risks stemming from a reduction in stability. The diagram shows instances of the model ship capsizing in tank experiments. You can see capsizing occurred around 1.5 when dangerous encounter wave grouping phenomena are more frequent. To avoid the risk of capsizing due to a reduction of stability, you need to have your ship sail clear of this dangerous zone to minimize the chances of riding on the crests of waves for a prolonged period. For this purpose, you also need to reduce the ship's speed or alter course, or do both to change the encounter wave angle. Broaching to is also one of the dangerous phenomena which can occur when a ship is sailing in following and quartering seas. Let's take a look at this phenomenon. Broaching to is a very dangerous phenomenon, often resulting from surf riding, in which a ship loses steerage upon being accelerated at the downslope of a wave in following and quartering seas. This is an extremely dangerous phenomenon, as the ship will lose steerage and turn abruptly with great centrifugal inertia, exposing her broadside to beam seas, often resulting in instantaneous capsizing. The broaching to phenomenon is considered to be caused by this surf riding. avoid surf riding, you should know the critical ship speed that causes this phenomenon. The critical speed that causes surf riding is considered to be 1.8 multiplied by root L. Therefore, you should reduce the ship's speed to less than 1.8 multiplied by root L. In addition, even before reaching the surf riding condition, to avoid large surgings likely to induce the broaching to condition, it's necessary to reduce the ship's speed to less than 1.4 multiplied by root L. The formulae shown here are also cited as the criteria for avoiding broaching to in the guidance adopted by the IMO. However, when a ship is sailing in shallow waters, a surf riding phenomenon can be caused even when a ship is sailing at a comparatively low speed. This should be borne in mind, in particular by seafarers operating high-speed pleasure boats and fishing vessels. To prevent encounter wave grouping phenomena, it's necessary to take care so that any combination of important factors, such as encounter wave angle, ship speed and wave period, do not fall in the danger zone. To prevent parametric rolling, it's necessary to take care so that the encounter wave period to the ship's natural rolling period ratio does not fall to half. To prevent a reduction of stability, it's necessary to avoid the ship riding on the crest of a wave for an extended period by reducing the ship's speed or by altering course. To prevent surf riding and broaching to, it's necessary to be aware of the critical speed leading to surf riding conditions. In addition, take special precautions to prevent these phenomena when a ship is sailing in shallow waters. For seafarers operating pleasure boats, high-speed fishing vessels, small and medium-sized ships, this should be particularly borne in mind. We hope this video helps to promote safe ship operations by reminding you to observe the basic ship handling requirements and by providing you with sufficient knowledge on the dangers of sailing in following and quartering seas. When a ship navigates in head seas, its hull is subjected to severe shocks which induce violent ship motions. As well-trained and experienced navigators, we are able to respond to this by altering the ship's course and speed as required. However, to accomplish safe navigation in head seas, it's advisable to have more reliable ship handling techniques backed by theoretical knowledge as to why these phenomena are created and how to avoid the generation of these critical effects, in addition to possessing seagoing experience. A ship at the mercy of wave forces heaves, pitches, and rolls repeatedly. Depending on the ship's relative position in waves and whether it's being lifted up to the top of a crest or falling into a trough, hogging, sagging, and twisting forces generate great deflections in the entire hull structure. In addition, the ship's speed is usually decreased by wind and wave resistance. This phenomenon is particularly augmented in head seas. So, let's take a look at a ship's pitching motion in head seas. This is the motion that has the greatest influence on the safety of a ship. Ship motions are insignificant when wave length is shorter than ship length because the effect of the wave is small. In this condition, the bottom of the bow neither rises enough to be exposed dangerously nor dips enough for the foredeck to take on water. When wavelength is longer than the ship length, a ship pitches and heaves slowly at the front and rear surface of waves corresponding to its form. When wavelength is equal to ship length, ship motions will be most intense. The heaving of the ship on a crest and the plunging of the bow into the succeeding wave will be accelerated. In such cases, changes of water level both forward and aft become particularly great in regular waves, and this causes propeller racing, shipping seas, and slamming phenomena. Whenever a ship pitches and heaves heavily at the bow, an equivalent heaving motion is generated at the stern. Due to these motions, the stern lifts out of the sea at intervals, exposing part of the propeller and causing instant increases of propeller revolutions accompanied by intense vibrations due to the abrupt reduction of propeller load. This phenomenon is called propeller racing and can have adverse effects not only on the propeller itself but also on the propeller shaft and engine. Therefore, we should make the stern draft as deep as possible so that the propeller immersion will be kept at more than 20% of the diameter of the propeller when navigating in rough seas. As resistance to the hull increases, the ship sometimes plows through the water under excess engine load. This causes what is called a torque-rich effect, and may often result in engine trouble due to overheating or in great waste of fuel. In such conditions, it's essential to reduce ship speed. Shipping seas is a condition in which a mass of green sea sweeps over the decks beyond the forecastle bulwark. A ship may sometimes suffer severe damage from the impacting green seas. Deck machinery, deck cargo and hatch covers are often damaged by the seas thus shipped, and hatch cover damage can allow the entry of water into the holds. These assaults by green seas have two effects: direct dynamic pressure from the shipped masses of green sea and the ensuing damage caused by the impact of sweeping waves against deck machinery and appliances. The dynamic pressure of green sea pounding on deck vertically may reach about twice that of shipped green seas. Furthermore, the dynamic stress of a sweeping mass of shipped seas over decks, increasing in proportion of ship speed to the power of 2, becomes almost as great as that from vertical pounding. Now let's observe the phenomena associated with a ship shipping seas using a ship model. The phenomena differ remarkably between angles of encounter of 0 and 60 degrees. The sea shipping phenomena differ remarkably between ship speeds of 9 knots and 3 knots, even if the ship is in head seas. As you have seen, shipping seas becomes more frequent when wavelength is equal to ship length in head and countering seas. We can decrease the chances of shipping seas by reducing speed or altering course. Next, let's study the phenomena associated with shipping seas when there are irregular waves. Waves usually encountered in the ocean are a complex mixture with different lengths and heights. Let's start the trial. In this case, the ship travels at a speed of 9 knots in head seas with an average wave period of 7.13 seconds and a wave height of 3.7 meters. Under these conditions, the action of the seas being shipped is violent. Let's change the angle of encounter of the ship to waves to 60 degrees, while leaving the other factors unchanged. Under this condition, rolling increases, but no seas are shipped. In summing up the results of these trials, it's clear that the frequency of seas being shipped increases in proportion to ship speed. When a ship sails at a relatively high speed in head seas, slamming may occur. Slamming can be broken down into 3 categories. Bottom slamming is caused by the interaction of a ship's bottom and the sea surface when a raised hull plunges into the sea. Bow flare slamming is caused by collision impact with the sea surface at a relatively high speed. Bow breaking wave impact is caused by breaking waves superimposed on built-up waves at the bow of a large, full-hull type ship in head seas. These forms of slamming phenomena often not only cause structural damage to bow, bottom or bow flare, but also lead to major cargo damage. As the frequency of slamming increases, there is the chance of cracks developing in the hull structure and of metal fatigue due to repeated stresses and strains, sometimes leading to a major casualty with a total collapse of the hull. Here, in a model ship trial, we study what conditions cause slamming to be generated. It appears that the frequency of slamming increases in proportion to ship speed. In addition, It's also clearly indicated that the frequency of slamming increases when forward draft is reduced. From this table, it's possible to calculate the necessary speed reduction to decrease the frequency of slamming by half. Propeller racing, shipping seas on decks, or slamming may be generated when a ship navigates at a relatively high speed in head seas. We have studied the frequencies of shipping seas and slamming on various types of ship based on the correlation between ship speed and encounter angle of the ship to waves. To avoid any critical situation, it's essential for the navigator to handle his ship by adjusting speed optimally based on correct knowledge of these environmental conditions, while taking his own ship's stability and maneuverability into consideration. A navigator's primary responsibility is to operate his ship safely in harmony with natural wind and wave conditions. Strong winds and heavy seas caused by a fully developed extratropical cyclone. Tropical cyclones and typhoons sometimes dominate the seas with devastating forces. What is expected for navigators to ensure safe and economical voyages in such a precarious natural environment? This shows clouds over Japan from the generation of a low pressure to its disappearance. Let's see how these lows generate and develop. The generation and the development of an extratropical cyclone are greatly affected by air masses in the near-sea areas of Japan. There are two air masses affecting the meteorological condition in the near-sea areas of Japan. One is the Siberian air mass, a cold air mass. The other is the North Pacific air mass, a warm air mass. Depending on seasons, the Okhotsk air mass and the Yangtze air mass also affected. When air masses with physically different characteristics come into contact with each other, fronts are created in the frontal boundary zone. When a warm air mass is predominant, the warm air mass moves towards the cold air mass and pushes the front forward with a lighter warm air creeping up the frontal boundary of the cold air mass. A front formed in this manner is called a warm front. Conversely, when a cold air mass is predominant, it moves towards a warm air mass, and the cold air mass moves the frontal boundary forward, raising the lighter warm air mass. A front formed in this manner is called a cold front. An extratropical cyclone generates on this front. If the warm air mass in the south of the front moves northward, and the cold air mass in the north of the front moves southward, an updraft occurs due to the contact between warm air and cold air masses. This generates a counterclockwise spiral flow of air growing into an extratropical cyclone. The larger the difference in temperatures between the two air masses in the north and south, the larger the extratropical cyclone. For these reasons, larger extratropical cyclones develop in winter than in summer. extratropical cyclones generally move northeast, approximately at a speed of 40 kilometers an hour and 10 degrees in longitude a day. The approximate maximum wind speed can be calculated using this equation. For example, if central atmospheric pressure is 1000 hectopascals, the maximum wind speed can be estimated at 15.8 meters per second using this equation of approximation. To understand meteorological phenomena caused by an extratropical cyclone, it's necessary to grasp the three-dimensional conditions of atmospheric air movement within the troposphere up to approximately 12 kilometers from the ground surface. Knowing the weather at the upper level within the troposphere shown in this chart is essential to learn the surface weather. Ships mainly refer to 500 hectopascals upper level charts. This is because levels of 500 hectopascals correspond to approximately half the average height of the troposphere, and its atmospheric pressure is about half that of the ground surface. These extratropical cyclones tend to generate in front of a trough in the upper level. When a trough deepens from the day before, a low develops on the surface below. We also need to keep an eye on the movements of upper-level isotherms because movements of upper-level cold air towards the south may cause extratropical cyclones to develop associated with gusts. Special attention should be paid to the movements of isotherms of 500 hectopascals upper-level charts at minus 30 degrees centigrade and minus 36 degrees centigrade in winter and minus 24 degrees centigrade in spring and autumn. As already explained, it's recommended that navigators should use upper-level and surface charts in an optimum combination. Lows generated in a tropical zone are called tropical depressions. In Japan, a tropical depression with a maximum wind speed of 17.2 meters per second or more is called a typhoon. Paths of typhoons generally come in two types: those traveling northwest after birth, and those recurving rightwards along the western fringe of the North Pacific Ocean high, then traveling northeast, influenced by westerlies. The path of the right-turn type is largely dependent on the strength of westerlies and the North Pacific Ocean high. Most typhoons at first tend to advance east, bearing on the North Pacific Ocean high in the 500 hectopascals upper-level chart at its right side, along 5,820 meters or 5,860 meters contour. Recurving points of typhoons may vary corresponding to the pattern of the ridge of atmospheric pressure of the North Pacific high extending east to west. Let's take a look at a few days of movements of one typical developing extratropical cyclone in the near-sea areas of Japan in detail, referring to related surface charts. In the near-sea areas of Japan, many extratropical lows generate from autumn to spring, and sometimes they develop to levels comparable to typhoons. They are categorized into three patterns corresponding to their origins and ensuing tracks as follows: East China Sea lows, the Japan Sea lows, and twin lows. After the low has moved east under the influence of these three weather phenomena, a typical pressure pattern of highs in the west and lows in the east is often established. Let's take a look at such a typical pressure configuration. a typical winter pressure configuration of highs in the west and lows in the east, as shown in this surface chart, appears from November to March. When the continental high extends to cover Japan and a developed low exists in the northeast area of Japan in the North Pacific, the winter monsoon grows stronger and lasts longer. In the areas east of Nojimasaki of Japan, marine casualties involving large ships have often occurred due to high waves caused by the winter monsoon, which lasts for a long time with long fetches over the sea surface. In addition, as the southern tip of the upper cold air passes this sea area, causing turbulent airflows due to convection caused by the big difference in temperatures between cold air of the upper layer and the warm surface layer over Kuroshio Current, wave heights increase. This is why unusually high waves generate over a wide area. This high wave area extends 30 to 37 degrees north in latitude and 140 to 160 degrees east in longitude. As this high wave area appears in the southwest quadrant, far from the center of the low, it's necessary to know the movements of upper layer cold air from the isotherms of 500 hectopascal upper level charts. It's necessary to know the relative position of a ship to the subject tropical depression or typhoon to minimize its effects. When a typhoon is moving north and wind direction observed on board changes clockwise, the ship is in the right semicircle of a typhoon. In contrast, if the wind direction changes to counterclockwise, the ship is in the left semicircle of a typhoon. The rate of change of wind direction is larger when the distance between the ship and the typhoon is smaller. Conversely, the change becomes smaller when the distance increases. A large change foretells abrupt and drastic directional change of wind direction. The semicircle to the right of the center line of the typhoon's path is called the critical semicircle, where original winds of the typhoon are enhanced by same directional prime mover air current. If a ship is in this semicircle, it will endure a pressing wind towards the center. On the other hand, the reason why the left semicircle of the advancing path of the typhoon is called a navigable semicircle stems from weakening typhoon winds due to the adverse prime mover current of the typhoon. And when a ship is in the right semicircle, the wind presses the ship behind the typhoon. Nonetheless, even in a navigable semicircle, as it accompanies a storm area, proper caution is necessary. Therefore, it is advised that the course is maintained to keep the wind at the starboard bow when in a critical semicircle, and at the starboard quarter when in left semicircle to turn away from the typhoon. Today, we can easily receive various maritime meteorological information such as surface charts, upper-level charts, ocean wave chart, and photos taken by meteorological satellites broadcast by the Meteorological Agency. It's important for seafarers not only to endeavour to acquire the necessary knowledge to make best use of this information, but also to have safe and cost-effective shipping operations. Narrow passages and fairways in rivers and canals, where the navigable depth or width is comparatively small in relation to the draft and the breadth of transiting ships, are called restricted waters. The maneuverability of ships navigating through such restricted waters will be affected by peculiar hydrodynamic effects that are different from those when ships navigate in broad and deep waters. These peculiar hydrodynamic effects that affect the maneuverability of navigating ships are the shallow water effects, ship squat, interaction, and bank effect. In this video, we intend to present the shallow water effect and ship squat. When a ship proceeds, surrounding water is displaced towards the sides and bottom, making a relative flow against the ship's advance. The advancing hull submerges deeper compared to when she's dead in the water. This changes the subsequent trim because the water around the hull flows a little faster compared with the ship's speed, and the hydraulic pressure decreases. This phenomenon is called ship squat. We shall see this phenomenon with a ship model in a tank test. The Froude number is an essential concept for a model tank test. To run a model at a speed corresponding exactly to that of a real ship, a ship speed is applied using this equation, which gives the same Froude number to different model lengths and the comparable real ships. Here you see a ship in a tank test. Let's take a look at the sinkage of the ship at her bow and stern. Let's also look at the subsequent trim change running in deep water by using a ship model in a tank test. This is the bow of a fully loaded small ship running in deep water, where the ratio of the depth to the ship's draft is 5.0 at 11 knots. This shows the condition of the stern of the same ship running at 11 knots. This is the bow condition when the ship's speed is increased to 13 knots. This shows the condition of the stern of the same ship at a ship speed of 13 knots. These curves are drawn based on the test results in deep water. As you can see, the sinkage of the bow and stern change like this as the ship's speed increases. The value in this graph represents the ratio of sinkage to the ship length. However, the sinkage at the stern of a merchant ship under normal speed is generally very small. By contrast, the sinkage at the bow appears larger compared with that at the stern. As you see here, a ship underway tends to show trim by the head. Now, using a tank test, we shall take a look at how sinkage at the bow and stern change when a ship proceeds in shallow water. This is a model of a small ship running in shallow water. The ratio of water depth to draft is 1.5 at a speed of 9 knots. This is the stern condition at a speed of 9 knots. This is the bow condition when speed is increased to 10 knots without changing any other conditions. This is the stern condition at a speed of 10 knots. As you can see, the sinkage appears larger at both bow and stern in shallow water. Now we shall see how sinkage changes depending on the speed when a ship proceeds in shallow water. For ship speed with a corresponding Froude number less than 0.25, sinkage at the bow is greater than that at the stern as the Froude number increases. However, sinkage at the bow stops suddenly, and that at the stern finally increases when changing trim by the stern as the Froude number approaches 0.25, which is close to the values in high-speed areas. We shall see this effect in shallow water and that in deep water. Sinkage at the bow in shallow water, which reaches 2% of the length of a ship, is larger than that in deep water. So, why do these phenomena happen? In shallow water, where the bottom clearance is comparatively small, the ratio of the horizontal flow along both sides of the ship increases because the current towards the bottom is restricted. The hydraulic pressure along both sides of the hull decreases, as the nearer the hull is to the surface flow, the faster the rate accelerates, and the water level around the ship drops considerably. For this reason, sinkage at the bow and stern and subsequent trim change become larger in shallow water than in deep water. We should be careful that sinkage at the bow and change of trim become greater when a ship runs in shallow water. Now we shall see how the depth of water affects a ship's turning capability in shallow water. Let's take a look at the data of the turning capabilities of large ships. Every curve indicates the tactical diameter of a specific ship by the multiples of the ship's length. This is a ship turning at 7 knots with a 35-degree rudder angle in deep water, where the ratio of water depth to draft is 6.0. This is a ship turning in shallow water, where the ratio of water depth to draft is changed to 1.5, while the other conditions remained unchanged. This is when the ratio of water depth to draft is changed to 1.2 without changing any other conditions. Now we shall see how the turning track differs as the depth of water changes. When the ratio of water depth to draft is 6.0, the turning tracks are as seen here. This is a conventional turn. Here is an accelerating turn. This is a coasting turn. When the ratio of water depth to draft is 1.5, the turning tracks are as seen here. This is a conventional turn, here is an accelerating turn, and this is a coasting turn. When the ratio of water depth to draft is 1.2, the turning tracks are as seen here. This is a conventional turn, here is an accelerating turn, and this is a coasting turn. Thus, we can estimate the tactical diameter of a ship running in restricted water as the multiples of its length. Although the presented data hitherto are taken from the test results of large ships, this method can also be applied to smaller ships. In view of the maneuverability of a ship, the depth of water also affects course stability, like the effects on turning ability. We shall study the difference of the effects on course stability in deep water and in shallow water from the results of zigzag maneuver tests. In the zigzag maneuver test, a ship's rudder starts to swing alternately to port and starboard when the ship is set on a steady straight course. At first, the rudder is put to starboard 10 degrees until her head swings starboard 10 degrees from her original course. Immediately after the ship's head swings 10 degrees starboard, the rudder is changed to port 10 degrees until her head points 10 degrees port from her original course. These alternate rudder operations are repeated several times, making a ship run in a zigzag course. These overshooting angles are called overshoot angles. Here you see the results of Z tests conducted in deep and shallow water. As you see, the required time to turn a ship's head port or starboard to a settled angle in shallow water becomes shorter with a smaller overshoot angle than that in deep water. This means that we can expect quicker rudder effect in shallow water compared to that in deep water. A well-remembered case among several cases reported in the past is that of a large passenger ship navigating in shallow water without reducing her speed that hit her bottom severely on the rocks. When running in restricted water, it's essential to keep enough under-keel clearance to avoid the deterioration of maneuverability and touch-bottom damage. Under-keel clearance means the space between the ship's bottom and the seabed. It equals the value when the ship's draft is subtracted from the sum of chart datum and height of tide at that time. To maintain enough under-keel clearance, we have to consider the factors affecting the sinkage of the hull, such as squat allowance, wave response allowance, possible error of chart datum, meteorological and oceanographic conditions, and other environmental conditions, and secure a safety allowance that eliminates ship handling difficulties. As we have studied in this video, the effects of sinkage and change of trim when a ship navigates in shallow water greatly affect the ship's maneuverability. Enough knowledge of these effects in restricted waters will prevent accidents.
In January 1934, the British battleship Nelson left Portsmouth for the open sea at 9 knots and went aground on a starboard shoal in a narrow channel due to the unexpected ship's response of swinging her head to starboard, despite the helm being turned to port 15 degrees for the intended course. The reason for this grounding was a typical bank effect. In restricted waters, where the navigable width of a passage is limited, ships are obliged to navigate close to a bare shore or artificial structures such as banks and bridge piers. In such a passage, ships also have to pass by or run in the same direction, while keeping minimum sea room from each other. Under such circumstances, a ship's motion may be largely affected by interference between two ships passing by and going in the same direction in close proximity, and bank effects due to banks, bridge piers and sea-bottom contours. In view of ship handling, ships are exposed to higher risks under such circumstances. Such phenomena affect any ship, regardless of size, when it enters restricted waters. We shall see how a bank effect acts on a ship's steerability. Even in a narrow passage, such as a canal, ships manage to maintain a straight course as they advance on the centre line of passage. By contrast, when a ship's track deviates to either side off the centre line of a passage, the ship moves with its hull as a whole being pulled closer to the bank, while its bow is repelled from the bank. On the contrary, water level rises up the bow because displaced water mass is accumulated in the confined space between the closer bank and the ship's hull. This water level makes a repulsive force to turn the ship's bow outward. This means the generation of a bow outward moment. The bank effect is a phenomenon that causes a bow outward moment and attracts the ship's hull as a whole to the bank due to decreased pressure at the midship area. This attracting force is called suction. Ship handling becomes very tricky due to the deterioration of course stability caused by the bank effect when a ship navigates a narrow channel, as we've illustrated. How should we handle a ship under such conditions? To have a ship run in a straight line on its intended course by offsetting suction and bow outward moment caused by the bank effect, the ship's head has to be kept obliquely to its intended course. As a result of this oblique posture to the advancing direction, extra force and turning moment will be generated on the hull. This extra force will offset suction to the bank. However, to offset bow outward moment, a checking rudder motion toward the bank is still required. This means that the turning moment and the force produced by the proper angle of checking rudder can offset the forces and turning moments generated by bank effect and oblique posture. To prevent contact with the bank at the stern, it is necessary for a ship to steer toward the bank. The ship can then maintain a parallel track to the bank. When there are multiple ships passing by, running abreast or overtaking in a narrow channel, the interaction between two ships moving in close proximity will sometimes have a grave effect on those ships. The effect of the interaction varies depending on the relative positions of the two ships. First, we look at the case of two ships of almost the same size passing each other. When the bows of the two ships come closer within the mutual hydrodynamic range, a strong repulsive force at the midships and bow outward moment are created. Alternatively, strong suction at the midships and bow inward moment are produced between two ships when they come abeam of each other. When the sterns of the two ships pass each other, these effects are transformed into repulsive force and bow outward moment. These effects of extra force and moment fade away quickly as the distance between the two ships increases. The results comparing the effects of interaction at 4 knots with those at 6 knots demonstrate that the interaction between two ships passing becomes larger and persists proportionally to ship speed. Two ships pass by in the opposite direction, a collision seldom happens because the influences of repulsion and suction last for a comparatively short time. However, it should be borne in mind that the risk of contact at the stern will increase if either of them should turn its rudder in the wrong direction inadvertently. The interaction between two ships of almost the same size running abreast in the same direction or overtaking in a narrow channel also varies depending on their relative positions. In this case, the risks of rear-end collision and contact increase because the interaction between the two ships lasts for longer. Let's see how an interaction is produced when ship A overtakes the other ship B when the intervening beam distance almost equals ship's breadth. The effects will be like these when the bow of ship A overtakes the stern of ship B. When ship A advances 1/3 to 1/4 of its length from the stern of ship B in parallel, the effects change like this. When two ships run abreast, strong suction at the midships and bow outward moments are generated between them. The effects will be like this when the bow of ship A advances ahead of ship B, but 1/3 to 1/4 of their hulls remain parallel. The effect will be like this when the stern of overtaking ship A comes abeam of the bow of ship B. Let's look at how the interaction between two ships in close proximity and running in the same direction in a narrow channel affects the steerability of a ship through a simulation. This is the case in which ship A overtakes ship B in a narrow straight channel with a width of 310 meters. The two ships are similar, and these figures represent the specifications of ship B. Ship A runs at 4.5 knots and ship B runs at 3 knots. The beam distance between the two ships is half of the ship length. The two ships are steered to maintain parallel courses. In this case, the length of ship A is 0.8 times that of ship B. Now let the lengths of the two ships be the same. Now let the length of ship A be 1.2 times that of ship B. As you can see in the results of the simulation, the interaction between the two ships is enhanced as the length of the overtaking ship increases. A collision occurs because the overtaken ship is pulled to the overtaking ship by suction when the ratio of the lengths of the two ships ranges around 1.2. Let's take a look at the effect of ship speed. In this case, the ratio of ship speed of overtaking ship A to that of overtaken ship B is 1.2, and the beam distance between them is half of the ship length. The two ships are steered to maintain parallel courses. The simulation is made by changing the speed of overtaking ship A, maintaining the speed of overtaken ship B at 3 knots. You will find that the risk of collision increases as the difference between the speed of the overtaking ship and that of the overtaken ship decreases. This is because the time when the two ships run parallel in close proximity is prolonged, and the subsequent interference between the two ships lasts longer proportionally. As you can see in the results of the simulation, there is a larger interference effect on an overtaken ship when the difference of speed of the two ships is small and the overtaking ship is larger than the overtaken ship. It becomes difficult for a ship to avoid a collision through its own steerability when this interference grows beyond its capacity. It is particularly important to maintain safe navigation in restricted waters such as ports and narrow passages where maritime traffic is dense and the risk of accident is high. When ships are obliged to move close to each other in such restricted waters, cautious ship handling, taking steerability of their own ships, the effects of interaction and interference between ships and bank effect into consideration are indispensable. Recently, accidents that have resulted in losses of anchors together with the entire length of anchor cables have been increasing while ships were attempting to anchor. Accidents involving ships lying at anchor have also repeatedly occurred. Most of these accidents involve drifting, collision and stranding caused by dragging anchor. We will study how to prevent drifting due to dragging anchor while lying at anchor and loss of anchor and its cable while attempting to anchor. When anchoring is anticipated, it is essential for mariners to acquire meticulous knowledge on the anchorage beforehand and select a sheltered, good holding ground with an appropriate depth, depending on the ship's own maneuverability and conditions, taking weather and sea conditions, dangers such as submarine cables, as well as pipes and wrecks in the vicinity into consideration. It is necessary to have a clear plan on how to reduce the ship's speed from the approach to the intended anchorage and how many lengths of cable are to be paid out. A method of riding to a single anchor is the most frequent anchoring method. However, the anchoring method should be decided depending on weather and sea conditions, and necessary preparations are carried out according to the selected method. The specifications of anchor and anchor cable to be stowed are decided by the equipment number of the ship. Each classification society also has its own requirements in compliance with this standard. Today, the AC-14 type anchor appears to be the most widely used, but there are various other types of anchor available. Let's look at the holding property of an anchor. The flukes of this type of anchor do not bite into the seabed as expected, and the anchor is easily overturned when stress is applied. What's more, once overturned, the anchor will never bite into the seabed again. These are the flukes of the AC-14 type. The AC-14 type is the most popular anchor today. It bites into the seabed well and remains stable without overturning when stress is applied. This curve shows the results of anchor pulling tests. Holding power is the resistance created by the anchor when it is pulled. The maximum resistance is called holding power. In addition to the holding power of the anchor itself, the effect of the cable paid out cannot be neglected. The total mooring power is the sum of the holding power of an anchor and the resistance of cable laid over the bottom. Although the anchoring method varies depending on the depth of an anchorage, lying at a single anchor is most frequent because of its handling simplicity, either when dropping or weighing anchor. In this pattern, the anchor is usually let go under sternway. First, we look at the procedure for lying at a single anchor in an area with depths to 20 meters. It is important for the running out chain to be checked by proper brake handling after the anchor is let go by free fall releasing the brake. Letting go the anchor and the cable without applying the brake properly increases the danger of loosing the anchor with all of its cable and damage to the windlass. Sternway just after letting go the anchor should be adjusted 0.5 to 1 knot to avoid imposing excessive strain on the cable in large vessels. And the brake should also be screwed up to stop the cable when the required shackles are sent out and have the anchor fluke bite into the seabed under sternway inertia. Next, let's study anchoring at a deeper anchorage depth of from 20 meters to 50 meters. In a deep area, the possibility of loss of anchor and its cable becomes greater due to excessive running out speed if the anchor is let go by free fall. avoid this hazard, the anchor is lowered by walking back into the water until it reaches about 5 meters above the bottom. Then the brake is released to let go the anchor, while applying the brake to adjust the running out speed of the cable and carefully maintaining proper sternway. When the depth of an anchorage exceeds 50 meters, the anchor and the whole cable required are laid down onto the seabed by the walkback method. In this case, sternway should be maintained under 0.5 knots once the anchor has touched the bottom, because too large a speed difference between sternway and walkback may cause parting of the anchor cable or damage to the windlass due to excessive strain in large vessels. The limitation of depth for anchoring cannot be decided only from the total amount of anchor shackles, and is limited by the rated capacity of the windlass. Generally, a windlass is provided with a weighing capacity of up to 3 to 4 shackles of cable, or about 82 to 110 meters. In an anchorage where the influence of winds and tideways are strong, there is a greater danger of dragging anchor due to excessive strain on the cable, otherwise due to the reduction of holding power stemming from a meandering cable caused by the effects of winds and tideways. Anchoring in wind at a wind speed exceeding 10 meters per second causes ship motions that draw a figure of 8 locus. The maximum tension on the cable during this motion occurs when the ship drops back from its extreme yaw to the position where her fore and aft align the direction of the cable against the wind, or a little offset point. This moment may be deduced from the change of relative direction of the wind on the navigation bridge. The anchor drags when it loses its grip on the bottom and starts sliding over the bottom. For a PCC or an LNG carrier with a large windage area lying at a single anchor, the critical wind speed is 15 meters per second. When the second anchor is dropped, the critical wind speed is 20 meters per second. And even when the ship is lying at 2 anchors, the critical wind speed is said to be 25 meters per second. Once an anchor starts to drag, it is difficult to stop. Personnel assigned to anchor watch are required to pay close attention to a sudden change of weather and must report it immediately to the master. They should pay careful attention to weather forecasts. A great advantage of anchoring is that ships can lie at anchor anywhere if there is sufficient room, sheltered from wind and sea, and provided with appropriate depths and good holding ground. Consequently, anchoring is the most convenient and common ship operation due to its simplicity and mobility. To prevent an accident resulting from dragging anchor and loss of anchor and cable, The personnel who engage in anchoring are required to do their jobs with sufficient knowledge of the anchoring system, including the windlass, as well as the necessary skills. In harbours and ports where manoeuvring areas are confined and shallow, there are many navigational restrictions. Therefore, ship operators are required to manoeuvre their vessels in accordance with the environmental situation. Additionally, when the entering and leaving of ports also involves berthing and unberthing operations, ship handling without assistance is not easy. This difficulty is due to the problem of directional control and course keeping, a direct result of poor steerability at low speed and the influence of wind and current. Under such circumstances, ship operators are required to use assistance in ship handling, assistance such as the use of tugs when necessary, in conjunction with their own full understanding of the manoeuvrability of ships, including the ability of rudder deflections to check yaw at low speed, and the stopping power of various stages of reverse engine revolutions. In addition to a ship's main engine, rudder and thruster, tugs are used for ship handling assistance in bays and harbours. Tugs are classified by propulsion type as follows: Voigt-Schneider propeller, VSP type, controllable pitch propeller, CPP type, and azimuthing drive propeller, Z type. In Japan, the azimuthing drive propeller type is the predominant tug. Such tugs are equipped with two steerable propulsion units that revolve 360 degrees. By controlling both the direction and revolutions of the propellers, tug assistance for ship handling is available in all directions and with varying thrust. The use of tugs is decided in accordance with ship handling requests, such as to control a towed ship's speed, lateral motion, and yaw rate. In pulling out operations, the tug's paid-out rope length is reckoned ranging from double to 2.5 times the tug's length, L. As the towed ship's size increases, still longer rope is used. This is the arrangement for assistance in lateral motion control by one tug. It is common to use this arrangement in combination with a bow thruster or with an anchor. This is the arrangement for assistance in lateral motion control by two tugs. This is the arrangement for assistance in pivoting motion control. In the tug operations, either the pushing or pulling method is used. The pulling method is needed for broad sea room. This method has the demerit of towing force decrease due to the impact of discharge current, but it has the merit of a flexible use of tugs. When a tug tows the stern of a ship, the ship's pivot point will be aft of the bow, about 1/3 of the total length of the ship. When the bow is towed, the pivot point will be forward of the stern, about 1/3 of the ship's length. As the point of action C exerted by the tug moves closer to the ship's centre of gravity G, the pivot point P moves farther from the centre of gravity G. Consequently, turning in a short round requires a circular manoeuvring area with a radius greater than GP plus half of L, with the turning centre at the pivot point P. That is, the farther the point of action from the centre of gravity, the smaller the turning radius. A ship under 1 knot headway then makes a 90-degree turn with the assistance of a tug pushing either the bow or the stern of the ship. It is known that pushing abeam the stern of a ship causes a relatively large kick-out. At the same time, however, it enables the ship to turn in a smaller manoeuvring area than if the ship were pushed abeam the bow. When a tug assists the pivoting motions of a ship under strong wind and current conditions, the operation of towing the bow in the direction of the wind and current requires a broad manoeuvring area due to the ship's increased range of motion. On the other hand, the operation of towing the stern against the wind and current is effective for pivoting in a small area. The ship will be in motion close to turning in a short round. Therefore, close attention should be paid to ship handling in manoeuvring areas with strong currents. In the handling of berthing ships, it is very important to control the ship's approach velocity as well as directional control. As a ship approaches its objective location, its headway should gradually be reduced and the hull inertia should be stopped at the predetermined point. On the assumption that the ship can employ braking power through the use of dead-slow astern engine, guidelines for speed reduction schemes for LNG carriers, PCCs and container ships are shown in this graph. This is a guideline for a speed reduction scheme for VLCCs. To prevent damage to the wharf and fenders, a large-size ship should reduce its headway to 0 somewhere at a distance of 1 ship length or ship breadth from the wharf, and then make a lateral move, berthing with the ship's heading kept parallel to the wharf. Wharfs and shore-based mooring facilities are usually designed assuming a berthing velocity of 15 centimeters per second. Actual berthing velocities are limited, however, and should not exceed 10 centimeters per second for ordinary-sized ships and 5 centimeters per second for large-sized ships. The function of mooring lines is to control a ship's motions and make the ship fast to a fixed position. Head lines and stern lines are used to control surge, sway, and yaw. Spring lines function to control drift. Moreover, since it's desirable that each line be extended as far as possible, it is necessary that attention be paid from above during berthing operations to ensure these maximum lengths. In cases of in-harbour ship handling accompanied by entering or leaving ports, ship handling without assistance is far from easy. In particular, the external force of wind and current has a great influence on keeping course and on changing course, on speed control, and on the directional control of ships. Taking the influence of external force into consideration, we are requested to implement berthing ship handling with the proper berthing approach angle and velocity, and to use assistance measures such as tugs and bow thrusters for ship handling. With the request of the industrial world for the rationalization of transporting and procuring expenses, Large-sized ships have been developed primarily in bulk carriers and crude oil tankers. In particular, the cost of transportation per voyage has been reduced because wide-beam, very large ships have been placed in commission. Then the remodelling of the stern shape aiming at energy conservation has brought an improvement of propulsive efficiency, gaining the maximum 2 knots speed increase with the same output power. On the other hand, these very large ships have still more magnified their manoeuvring characteristics, viz. Good turning ability, but poor course-keeping ability. When manoeuvring very large ships, as typified by VLCCs, ship operators are particularly required to grasp exactly the manoeuvrability of their own ships and to establish manoeuvring techniques more than ever, including speed control. To attain the above challenges, let us consider how to deal with the manoeuvrability of very large ships. Good turning ability, stable course-keeping ability, and good initial turning and/or course-changing ability are required for ship manoeuvrability. But turning ability and course-keeping ability are of countervailing nature to each other. Turning ability is characterized by the radius and the rate of turn on the orbital motion of steady turning phase, the former being normalized by the ship length, and the latter by the turning speed and/or ship length. The initial turning and/or course-changing ability, hereinafter called initial turning ability, is defined by the change of heading response to a rudder deflection and the yaw damping response when the rudder is deflected to midship. In other words, this ability indicates whether steerability is favorable or not. The course-keeping ability is the ability to maintain a straight path with the rudder held midship, without applying any counter-rudder. The parameter of block coefficient CB is used for comparing fat ships and fine ships. Fine ships with small block coefficient, such as container ships, constitute characteristic features with good initial turning and course-keeping abilities, but with poor turning ability. On the other hand, fat ships with large block coefficient, such as tankers and bulk carriers, constitute characteristic features with good turning ability, but with poor initial turning and course-keeping abilities. First, let us consider the turning ability. When the rudder is deflected and held at a fixed angle, the turning path of the ship's center of gravity is called the turning circle. The advance is the distance of the ship's center of gravity along the original approach course from the start point of rudder deflection to the point where the ship has turned 90 degrees. The transfer is the distance from the original approach course to the ship's center of gravity when it has turned 90 degrees. The maximum advance is the maximum distance of the ship's center of gravity along the original approach course when the ship has turned a little more than 90 degrees. The tactical diameter is the distance from the approach course to the ship's center of gravity when it has turned 180 degrees. The maximum transfer is the maximum distance of the ship's center of gravity from the original approach course. And the final diameter is the diameter of the ship's trajectory when it has settled down to the steady turning motion. The reach is the distance along the original approach course from the origin of rudder deflection to the center of final diameter. Immediately after the completion of rudder deflection, the ship's centre of gravity and aft terminal are kicked out. The kicked out amount on the centre of gravity is about 1% of the ship length, but that amount on the aft terminal occasionally reaches more than 15% of the ship's length. The tactical diameter, TD, in a water area unaffected by water depth is shown in the figures, with the maximum 35-degree rudder angle. A fat ship, such as a tanker, is approximately 3 ship lengths, and that of a fine ship, such as a high-speed freighter, is approximately 4 ship lengths. Let us examine the influence of water depth on the turning circle, taking examples of a 280,000 deadweight ton tanker in full load condition. When turning in a shallow water area, the maximum advance increases approximately up to 1.4 times, and the tactical diameter up to 1.3 times, as compared to the turning in deep water respectively. Sufficient care should be taken for the above when navigating in shallow water straits such as the Malacca Strait. Let us examine the turning ability of a 280,000 deadweight ton tanker in ballast and in full load condition. When turning in full load condition, the maximum advance increases approximately up to 1.3 times, and the tactical diameter up to 1.2 times, as compared to turning in ballast condition. VLCCs and bulk carriers should be drawn attention for the changes of turning circles, as they may extremely change their condition, such as draft and trim, dependent on full load or ballast condition. When a rudder is deflected while a ship is advancing on a straight path, the ship begins to turn slowly at first, then increasing its turning rate gradually, and finally turns steadily with constant turning speed and turning rate. At the steady turning phase, the relation between the rudder angle and the steady turning rate is expressed as shown in the figure. Coefficient K is called the turning index gain, and the time needed for the turning rate to develop into 63% of steady turning rate is expressed as T. Coefficient T is called the initial turning index, time constant. Ship A and Ship D belong to the type that both course-changing ability and initial turning ability are either good or poor, and ships belonging to the above patterns are very scarce. Ship B has good initial turning ability but poor course-changing ability. Fine ships of high-speed freighters such as container ships belong to the pattern. Ship C has poor initial turning ability, but good course-changing ability. Fat ships, such as VLCCs, belong to the pattern. The control of a very large ship will become increasingly difficult when a turning rate has been fully developed with a large amount of rudder deflection. It is important to control the turning rate appropriately by putting over the rudder bit by bit. There is an example of providing an indication of turning rate control where the turning rate should be controlled within 10 degrees per minute for 10 degrees rudder deflection, or controlled within 20 degrees per minute for 20 degrees rudder deflection. Let us consider a case where a ship is changing its course. Due to the turning lag, it is unable to bring the ship on the intended course-changing path if the rudder is put over when the ship has reached the course-changing point. When changing course, the rudder should be put over before reaching the course-changing point, taking the turning lag into account. The course-changing distance is the distance along the original approach course from the start position of rudder deflection to the course-changing point. The relation between the course-changing distance and the course-changing angle is expressed as shown in the figure. Ship operators are required to acknowledge the elements of turning ability of their own ships, such as the amount of reach, the kicked-out amount on the stern, and the course-changing distance. The following are simulated cases when two full-load 280,000 deadweight ton tankers are meeting on reciprocal courses. In spite of each taking collision avoidance action by hard over helm to starboard, the collision was unavoidable, resulting in contact with each stern. In this case, each has commenced the initial evasive action at the bridge-to-bridge distance of approximately 0.8 nautical miles. With the assumption that a ship is approaching a berth with a decelerating maneuver, the diagram of speed and distance run is shown in the graph after the main engine stopped when the ship is making 6 knots. Approximate distance run until the speed is reduced to 2.5 knots after the main engine stopped can be obtained from the diagram, because the ship speed of 2.5 knots corresponds with the critical speed at which the rudder effectiveness is nearly lost. The time elapsed for speed reduction is also shown as a function of displaced weight and distance run. When approaching a berth with excessive speed, an order for full astern is required for stopping the ship. During the maneuver, the discharge flow of the backing propeller from the lower part impinges strongly on the stern plating on the starboard side, which tends to move the stern to port. Eventually, the ship's head turns to starboard, and it will become harder to keep directional control. In accordance with the Standards for Safety Management System, or SMS, the following precautions are required for decelerating maneuvers approaching a berth in harbour or an anchorage outside harbour. The ship's speed should be reduced gradually so as to be suited to the remaining distance. The ship should not overrun the target place, and the ship should be brought to stop with directional control being kept stable. Taking safety allowance into consideration, the speed reduction scheme for VLCCs on approach manoeuvres are shown on the graph. In approach manoeuvres, it is desirable to manoeuvre the ship within the speed range of recommendable in the graph, where the function of headway control and directional control are certain to be possible. Ship navigators who have never experienced the handling of very large ships are requested to understand the maneuverability of their own ships. The motion of very large ships cannot be controlled only by the conventional sensitivity of ship handling. Therefore, such ship handling, including directional control, is advisable, as using verified numerical data for maneuvering and the indication of a yaw rate meter. Recently built very large ships are characterized by good turning ability, but extremely poor course-keeping and initial turning abilities. It is to be hoped that you keep safe ship handling in mind, firmly grasping the above maneuvering characteristics. Such ships as represented by a pure car carrier or a car ferry are characterized as a special ship form with high freeboard, having a very large area of the hull and superstructure above water as compared to that of the underwater hull. Due to the above, the wind has great influence on the hull, and the wave from the bow has also much impact on the large flare of the bow. Particularly when a typhoon or a developed low pressure is approaching, there can be the case of unmaneuverability due to the ships being buffeted by strong winds and waves, the degradation of rudder effectiveness by heavy rolling and pitching, and speed reduction by propeller racing that may cause difficulties of main engine control. Besides, incidents of dragging anchor due to strong winds often take place while anchoring. Therefore, it is important for ship handling of PCCs to grasp wind effects and understand the maneuverability limits they impose. To carry as many cars as possible, the PCC is designed as a rectangular type hull structure with high freeboard, having an enormous area of the hull and superstructure as compared to that of underwater hull. Since the hull form of PCCs is quite different from that of tankers and container ships, PCCs are highly susceptible to wind effects at any time, whether in loaded or ballast condition. Let us start with the area that is susceptible to wind effect. The wind-affected area varies with the change of draft. The projection of above water on midship section of the full-sized PCC in recent years has the value ranging approximately from 950 square metres to 1,050 square metres, and that on lateral plane of symmetry from 5,500 square metres to 6,200 square metres. Let's compare the ratio of the projected area of above water portion to that of underwater portion by ship type. 3 model ships, each in loaded condition, are compared with the ratio of the front projection of above water portion AA to that of underwater portion AW, and the ratio of side projection of above water portion BA to that of underwater portion BW. The wind effect on the PCC is about 1.2 times on the front view and 1.5 times on the side view, respectively, as compared to that on a container ship. It is also known from the table that the wind effect on the PCC is about 2.6 times on the front view and 3.6 times on the side view, respectively, as compared to that on a tanker. So the PCC is highly susceptible to the effects of wind. Next, the resultant wind force is examined that has great influence on the maneuverability of a PCC. The wind force acting on each portion of the hull differs according to the shape of the hull and the wind direction. However, ship operators on the bridge deal with each local force as integrated. In other words, this unified force is termed the resultant wind force acting on the working point. The working point of resultant wind force is located at a distance of A from the bow and moves with wind direction. When the relative wind direction is in the direction of the bow, the working point is at the position nearest the bow, moving abaft as the angles of relative wind direction of the bow increase. The resultant wind force acting on the working point varies with wind speed and direction, reaching a maximum when the beam wind is acting on the largest wind-affected area. In the case of a PCC, it can reach 290 tons under the wind speed of 25 meters per second and the relative wind direction of 90 degrees. Now let us examine leeway. Needless to say, as the ship is being drifted on the leeward little by little, deviating from its planned course line, it is required to steer a little more to windward than the planned course in anticipation of leeway. Due to the above, when navigating a narrow channel whose width is confined under the influence of wind and tidal current, prudent ship handling is required in consideration of leeway. For this purpose, the ship is required to take a little more windward course than the planned course in order to remain on the planned course line. Leeway increases as the wind speed grows stronger or the ship is making less speed. In this case, ship handling is required to adjust the leeway by checking the ship's position frequently. When the wind speed is increasing, or the ship is making less speed, the outcome of the magnitude of leeway with the rudder held amidships is shown in this graph. Now let's examine the controllability limits of each type of ship when the maximum rudder deflection is limited to 30 degrees. As we can see, a PCC has a narrower region of controllability than other types of ship. For example, the critical wind speed on the tanker in ballast condition is 5 times as much as the ship speed, but that on the PCC is approximately 3.6 times as much as the ship speed. Now let's examine the turning of a PCC under a strong wind. As shown in these figures, the turning of the PCC is greatly influenced by wind. Due to the above, as the VA and VS ratio develops into 4, there are instances where the ship can be led to the region of uncontrollability depending on the relative wind direction, and some PCCs have extreme difficulties for turning maneuvers. For the above reason, it is necessary to grasp the maneuverability limit of one's own ship. A ship at anchor will swing around the anchored position in the wind, moving as if to draw a figure 8. First, the ship begins to be swept away backwards subsequent to its heading on the wind at the extreme end of the windward turning. Then, due to the backward motion and the turning moment on the leeward with the heading nearly unaltered, the cable tension greatly increases due to tension by wind force, and that by inertia force by the ship's accelerated motion. Now let's look at the relation between the wind speed and its force under the swing motion of the ship by wind direction. As shown in the graph, when the wind of 15 meters per second is blowing, the wind force is about 8.4 tons with the relative wind direction of 0 degrees. But the wind force increases to about 52 tons with that of 30 degrees off bow. Thus, it is shown that the wind force acting on the hull grows much greater as the angle of relative wind direction off bow increases. According to on-site reports from masters, when the ship is riding to a single anchor, the maximum angle of relative wind direction in degrees under swing motion is reckoned empirically as approximately double the wind speed in meters per second. The safe measure for preventing dragging anchor is how to control the swing motion of a ship while a full length of cable is paid out for the increase of its holding power. To control the swing motion, a swing check anchor is used with another anchor lowering to some 1.5 depths of water on its cable. This method can reduce the magnitude of swing motion on the order of about 50%. As examined so far, because the modern pure car carrier has a disproportionately large above-water hull and superstructure compared to its underwater hull, the ship is greatly influenced by wind force, and there is the extreme danger that the ship may lose maneuverability under its own power and equipment. When the ship is navigating a stormy sea area, ship operators should recognize the limit of maneuverability caused by the wind. It is also important that the early navigation avoidance should be made in ample time, particularly when the ship is reducing its speed for entering or leaving port. The wind effect grows even stronger. Therefore, depending on the situation, the ship operator is requested to aim at the safe operation of the ship, such as requesting tug assistance if necessary.